Let's quantify the errors that we have observed in terms of these tables. We saw actually plots of this error before. So using first order Euler method, which is the simplest method that we have talked about, and using 10 points, 20 points, and 40 points across the interval 0 to 2 pi, which gives us step sizes of these numbers. This is basically 2 pi over 10 and 2 pi over 20 and 2 pi over 40. That's what those numbers are. And we can see what the errors turn out to be. So the 2 norm of the error is indicated here. 1 norm of the error is listed here, and the infinity norm is listed here. And the striking thing you can observe is that for a solution which is of order 1, solution is varying between +1 and -1, we are getting RMS errors which are very substantial even when we have 40 points that are used to integrate the solution. And that's true of the 1 norm, the max norm, as well as the infinity norm. These errors are large. Errors are decreasing as we increase the number of points we are using. As we reduce the step size, errors are decreasing, and in fact for first order Euler method, these errors are decreasing in proportion to the step size. It's behaving as you would expect, but errors are large. And so there is this qualitative behavior that we are observing here, which requires some thought. Why is it that errors are large in this case, whereas in previous illustrations we found that at this kind of resolution we had many more digits of accuracy. We had 2 or 3 digits of accuracy, but here we barely have the first digit accuracy. And this is because in the present case we have an oscillatory solution, and so if you think about eigenvalue analysis associated with the system, the eigenvalues of the system are imaginary. It corresponds to oscillations, and if we do numerical analysis of the behavior of this scheme, we would find that for oscillatory systems, first order Euler discretization is actually unconditionally unstable for purely oscillatory problems. And so here I have computed these errors over this time horizon of 2 pi, but if we go to larger times, these errors will grow, and they'll grow unbounded as we go to larger and larger times. And so this is not a method that one should use because it is unstable for oscillatory problems. It's a perfectly stable method for monotonic solutions. For growing or decaying solutions, it is perfectly good. But of course, in practice, we may not know, or we may have mixed behavior where the solution may grow or decay and may also oscillate. And so we need to choose the method more carefully. And so if we actually use the second order Euler method on the same problem of this cosine wave oscillation, we find that in fact the error decreases dramatically. This is able to produce a very significant improvement, and in fact a second order Euler method is stable, conditionally stable for this problem, as can be shown by a further analysis, and that's seen practically in terms of the performance. In terms of error, that error is significantly less, and if we plot error as a function of time, we will see, or as a function of position here, as a function of this independent variable, we'll see a dramatic difference between these two solutions, as we saw in the plots before we started looking at these numbers. So having looked at this very simple example, let's consider a more interesting example where the equation has coefficients that are varying in space. And so we are taking one of the celebrated equations, the Bessel's equation, which is actually very simple, as you can see here. This equation you have encountered before. And we have the initial conditions that the value of the solution is 1 and its slope at 0 is equal to 0. And so if you recall the analysis or definitions associated with the Bessel functions and so on, you would be able to recognize that solution to this differential equation subject to these two initial conditions is in fact exactly the J0 Bessel function of the argument x. So this analytic solution is the solution to this differential equation, which we can use to assess errors. Of course, how do we numerically integrate? We of course rewrite this equation so that y double prime can be obtained as a function, and then we can rewrite this equation as a system of first order equations as we did before. And the only difference compared to the pure cosine oscillation that we discussed is that we have an extra term here where we have minus y prime divided by x, and then of course we have minus y, which we had for pure cosine. And so in this sense, from the equation, we can see that this equation is a modified equation. If we didn't have the first term, we would have a cosine oscillation. And as we can say that Bessel functions are cousins of sines and cosines, and that's something that shows up in the differential equation directly. All right, so we can integrate this, and I recommend that you integrate this using your favorite method. For example, a very simple method, first order, to integrate first order ODE system, such as the first order Euler method. You can program it and integrate it and see what you find. And here's the reference solution, which you can compute using MATLAB for different arguments x, and you can judge how accurately you are computing this. So I recommend that you try this out and see what you get. This is, it may look like it's a very simple example, but it's a very worthwhile example, and you will learn a lot if you try to do this yourself.